Can people hear me all right?
Yes.
Yep. Should I see if this works? Perfect. All right, thank you very much. I know that everyone's tired. It's a Friday, so I'm going to try to do this as quickly and painless as possible. So today I'm going to be talking about some of the work that we've been doing for how to use variational quantum algorithms for quantum metrology and quantum sensing tasks, and specifically how we're going to try to estimate the quantum feature information. So I'm going to be mainly talking about those three papers that you see right there. So the outline is very briefly, I'm going to be talking about quantum sensing and quantum feature information. Why are they important? How we present novel bounds for the quantum feature information, and the algorithm that we use to use those bounds to prepare good quantum states for quantum sensing. And then, quick outlook. So why do we want to do quantum sensing? I think at this point, this question is redundant, but for me, what's actually interesting is asking the question, with current technologies, we already know that noise can be an issue because quantum systems are extremely sensitive to interacting with their environment, right? And this is precisely the bane of quantum computers, where we're trying to constantly limit the quantum systems interactions with the environment because they are too sensitive to their environments. But on the other hand, this is precisely what we want to try to exploit in quantum sensing, that sensitivity and that fact that, you take a quantum system, it is going to interact with the environment. Let's as well try to use that to learn something about the environment, right? And of course, we know that this has several very interesting applications that we would like to exploit. So let's talk about the standard quantum sensing setting. I know that we just trashed this setting in the previous discussion about quantum sensing, but I still want to go here because there is a surprisingly reduced amount of literature on sensing for non-ideal cases, right? So we know that if you do like magnetometry with pure states, it's just GHZ and measure parity and that's it. But you veer away a little bit from that setting and it becomes very difficult. So we're going to take a quantum system, we're going to make it interact with an external source that's going to encode one parameter. In this case, we're going to consider like magnetometry or thermometry, but we're going to focus on magnetometry. And we also know that the ultimate sensitivity that our quantum states is going to be able to achieve is bounded by the so famous quantum Kramer-Rao bound, right? Where this thing that is in the denominator is the quantum Fisher information. So if we just take a look at the functional form of the quantum Fisher information, we're going to get these different terms right here, and if we look closer at them, the first one is taking this f function, which of course is the fidelity, but I'm going to get there in a second, between the state where you encode an actual parameter theta and a state where you encode theta plus a small deviation delta, right? And essentially what you want to try to do is have a state that is very sensitive to that small parameter change delta, right? Because if I have a quantum state rho that is exactly the same for all the values of theta and or delta, then this is a very poor quantum state for sensing, right? Because it's completely insensitive to that thing that I'm trying to measure. So in general, what we're trying to do is work with the quantum Fisher information, and we're trying to maximize the quantum Fisher information, right? And that means minimize the fidelity between the state, the exact state and the error state, because minimized fidelity means that they're more distinguishable the more your state changes with that parameter. But of course, the problem is that, if we just look at this formula for the fidelity, we cannot exactly compute this quantity if you have mixed states, right? If you have pure states, it's just going to be an overlap. So this is very simple to compute in a quantum computer. But in general, there are no quantum algorithms that can give you the fidelity exactly to arbitrary precision because it's a nonlinear function of your density matrix, right? And this is going to be an issue. So the question is, all right, so we want to try to work with the quantum Fisher information. That means working with the fidelity, but we can't really work with the fidelity, right? So what can we do with this? You can try to take this, do a Taylor series expansion, but you're going to need more and more copies of your quantum state for that. So we're trying to avoid Taylor series expansions here, right? So the question is, how can we try to still work with this idea that we want to try to optimize over a state that maximizes quantum Fisher information, minimizes the fidelity, but we cannot access the fidelity? Well, let's just think about creating bounds on the quantum Fisher information, right? So if you cannot compute them, bound them. So very quickly, I'm going to present two different bounds that we found for the quantum Fisher information. One of them is what we call the sub-quantum Fisher information. So it's this formula right here. I know that this doesn't tell you anything without saying who G is. So this quantity G right here is called the super fidelity, and it was introduced in this really beautiful paper right here. And what it does is that it is a lower bound for the fidelity, right? Upper bound for the fidelity. So what's really nice about this quantity is that all the different terms that you have right here can efficiently be computed in a quantum computer because it's just the trace of a product of two quantum states that we can do with a Hadamard test or a swap test, if you will, right? So every single term here is efficiently computable. And we know from that paper that the super fidelity is an upper bound for the fidelity. So that means that that quantity that we have up there, the sub-quantum Fisher information, is a lower bound for the quantum Fisher information, right? And that's that property that I have right here. I also have another slide with another bound that we presented that I'm not even going to discuss because it's Friday. So, but the most important thing is, up to this point, I just defined this quantity. Why is it interesting? Because we proved a lot of very nice properties of the sub-quantum Fisher information. So the most important one is that the sub-quantum Fisher information is a faithful bound. That means that it shares the extrema, the global extrema, with the quantum Fisher information. So of course, it's very easy to prove that they're going to vanish at the same point. That's almost trivial. But more interestingly, we can prove that they share the optimal state for mixed states. And this is a non-trivial statement because actually the optimal state for the quantum Fisher information for unitary families, where you encode your parameter with this e to the I theta h, was just discovered in like 2019 paper. So it was very recent that people discovered what is the optimal state for the quantum Fisher information. And what we proved is that our lower bound also shares the same optimal state. So that means that if you're trying to prepare a good quantum state using the sub-quantum Fisher information as a proxy, and you maximize it, you are guaranteed that you're also maximizing the quantum Fisher information. This is a really nice property because we can then use this for some sensing task where, we have our quantum state, we're gonna encode a parameter, put that in a quantum computer, and we're trying to maximize the quantum Fisher information, right? We cannot compute the QFI, let's compute the sub-QFI, and if we prepare a good state for the sub-QFI, we have a guarantee that it's gonna be a good state for the quantum Fisher information, right? And again, the sub-QFI can be computed with this circuit right here, plus classical plus processing, so that's a depth 2 circuit for any number of qubits, so we're not gonna incur in a lot of noise by computing that overlap. So very quickly, I'm not even going to talk about NISQ algorithms or what variational quantum algorithms are. I think that we've been talking about this for a while. So I'm just going to present the overall scheme. We take some input state that is easy to prepare, and you're going to send it through a parameterized quantum circuit that is parameterized by alpha. This is the encoding part of the circuit where we're trying to rotate our easy to prepare quantum state so that it is a good sensor. Then we're going to do this thing of encoding theta plus delta, and we're going to use our lower and upper bounds to try to get a good estimate of how good of a quantum state, how good of a quantum sensor this state is, right? And we're just going to optimize over those bounds by trying to do this maximization property of trying to maximize the sub-quantum Fisher information, because if you have a lower bound for a function and you maximize the lower bound, you sort of have a guarantee that the upper bound itself, so like the thing that you're lower bounding is also going up, right? So these are some numerical examples where we have some quantum state that has different amount of purity. So, the purer the state, the easier it's going to be to reach the maximum. So this is the Heisenberg limit. This is the theoretical maximum that you can reach for a state with this amount of purity. And this is what we're doing with our optimization, right? So you can see that the different plots from left to right is from one of the bounds. So we can just look at this one because we have one bound that becomes better the more work you put into this. But we can see that with a significant amount of work, we can prepare good quantum states for quantum sensing, right? And just to wrap things up, what we have is that we don't only have lower bounds that we can optimize over, we can also have upper bounds. And once you have lower and upper bounds, you can get an actual sense of where your quantity lives, because just a lower bound or just an upper bound is pretty much useless, right? But if you have two bounds or a family of lower bounds and a family of upper bounds, you're going to get a good idea of where your state lives, right? And what was interesting is that the only other lower bound for the quantum Fisher information that people knew was this orange line that was right there, and which was a terrible bound that people were optimizing over. But now, we have the green and the purple points, which are our two lower bounds, and the blue and the red points, which are our upper bounds. And you can see that, they provide good ranges where we have a very good idea of where the quantum Fisher information lies. So, I just want to say that this is what we've been doing. Some of the things that we want to try to generalize is all variational quantum algorithms need a parameterized quantum circuit. How do we build a good parameterized quantum circuit for a sensing task, right? Can we put information into that ansatz? Can we do it with short depth circuits, right? How can this be generalized to multi-parameter estimation, right? So that's also something else that we're interested in. And with that, I just want to thank my collaborators and acknowledge the Quantum Science Center and the funding that I got from them. And thank you very much.
Question?
That was 10 minutes on the clock. That was
Beautiful. Beautiful.
Yeah, I just wanted to make sure. So you had a statement where you said that it was 2019 people figured out what the optimal state was. What do you mean by that?
So what is the optimal state? So you have a state that is mixed, right? So it has a given purity or a given spectral decomposition. And you're trying to use it to estimate a parameter that is encoded with a unitary pattern, so e to the minus I theta h. And depending on the purity and that Hamiltonian h, your optimal quantum state is going to change. And this is a paper that rigorously proved what's the form of that state in terms of the eigenvalues and eigenvectors of that h. So magnetic field is just summation of z's, and the Heisenberg and the GHZ state is just equal superposition of the highest eigenvector and the smallest eigenvector, highest associated with eigenvalues. So sort of a similar idea holds whenever you have mixedness. You're going to have pairings of the state that has like the largest eigenvalue with the lowest, and then you're just going down the ladder. You have to be careful a little bit with some stuff that you do with the eigenvalues because degeneracies can be an issue. But they have a rigorous proof that that's the best that you can ever possibly do given a quantum state that has a given spectrum. I don't remember, and I actually noticed that I forgot to put that citation in here. Then it's like, if you look like optimal mixed states for quantum sensing, it's a PRL paper, it's beautiful, and the proof is very intricate. We talked to them because we didn't really understand it, and we're like, how did you derive this? And it was just trial and error. So it's a really good proof once you sort of understand it.
Sure.
On that same topic, by going through any of these variational procedures, are you able to develop, or have you developed kind of intuition for important properties of these states, whether they're optimal or close to optimal?
Right.
Important containment structures.
So this is actually interesting, and we're finishing a paper where we're looking at sort of that question, and we've realized that there are a lot of good quantum states for a given quantum sensing problem, and it's going to depend on what is your region, your parameter region of interest, right? Because if you have mixedness, you have some noise in your system, you're not going to have a pure state. It's going to happen that your states, whenever you measure some polyobservables, they're not going to be able to reach -1 and right because it's bounded by the purity, right? But if you care about a small parameter region, because you're trying to do like high sensitivity, high precision, or small changes in your parameter, you can actually get away with reaching the Heisenberg limit in small parameter regions, even whenever you have like noise and mixedness. So there is actually quite a lot of freedom in things that you can do if you restrict your problem to, this is the only thing that I care for. I don't care about reaching the Heisenberg limit across all my parameter range because I just care about this small region. Then that allows you way more freedom of the states that can actually reach the Heisenberg limit, which are absolutely not the GHZ state, for a magnetometry task. So yeah, it's not fully characterized at this point. It's mostly heuristic, but we're trying to develop some theoretical understanding of those problems.
So then a little follow-up on that. If you have this kind of distribution of states that all are able to give you sensing, do you have any sense as to whether there's a large distribution in the cost for state preparation of those?
So something that we're doing is, for instance, we're just restricting ourselves to things that can be prepared to log depth. So, we're not going to deep circuits because we don't want to have other issues because we don't have good ansatses and Brown plateaus and whatnot. So definitely with like short depth, you can prepare fairly good states. So again, like there's a lot of freedom. Not really sure how I understand it. And the other thing is that if you care about small parameter regions, you can go away with a lot of noise. So you can have states that have very small purity and still be able to beat the standard limit, the standard shot limit. So, they're going to be somewhere in between, but they can be very noisy. So, there seems to be a lot of freedom there.
Cool. Thank you very much. So I think Nick Bornman's next.
Yeah, can you hear me?
Yes.
All right, cool. Let me just share my screen. Can you see my screen?
Yes.
Yep.
Oh, cool. Cool. Yeah. Hi everyone. Yeah, I guess I got the coveted last spot of the day. On the last day of the workshop, but I don't think my talk is going to be too technical and it's a little bit left field, so I don't think it's too bad. My name's Nicholas Bornman, and I'm a postdoc at Fermilab in the SQMS Center. I'm part of the co-design efforts, so sort of trying to straddle the divide between theory and experiment and the hardware. And yeah, I guess a lot of people have chatted over the last couple of days, very technical talks about you know, how you can use quantum computers applied to you know, quantum chemistry and high energy physics problems. But another real world application that people predict quantum computers will be very good at is in the finance sector. So this is, I'll sort of spend a couple of 2-3 slides talking about some problems in finance that the financial engineers go about tackling. Then 1 or 2 slides talking about the quantum algorithms behind them, and then finally make some comments at the end about the qudit-based platform which Fermilab is trying to develop, and how there may be 1 or 2 advantages in a qudit-based platform compared to the, you know, a qubit-based quantum computer. Yeah, but there's a lot of open problems in finance. They're very complicated, very stochastic in nature. One common problem that people go about trying to solve, or one common problem in finance quantity that people often want to work out, is doing a risk analysis. So let's assume that one company takes a particular market position and is able to analytically work out, or at least infer, what the probability is of making a profit or a loss based on a particular investment or market position. That can even scale down to a person. And if a person buys or sells a particular asset, then they try and work out what is the probability of making a profit or a loss on that asset. And in a risk analysis perspective, a common quantity to quantify risk, which people work out, is called the VAR. So it would be the variable at risk, given some tolerance or given some confidence. I've just chosen 10% randomly here. So in the VAR, variable at risk, is typically would quantify the smallest amount of money that would be lost in this case, the 10% of the worst case scenarios. Another problem is derivative pricing. So a derivative contract is just a contract which derives its value based on other underlying assets or equities. So let's say a particular party is going to buy or sell an asset at some time in the future. Entering into that contract will have value, but the asset's value in the future wouldn't be known deterministically. It would evolve stochastically. And so what derivative pricing concerns itself with is trying to work out what the expected payoff is for buying or selling a particular asset or basket of assets at some time in the future. Because knowing that, you could then work backwards and work out what the price of the contract in today's values or in today's money should be. And finally, also portfolio optimization. So there's a number of assets, debts, equities that a person can purchase, which would be all terribly correlated with one another. Portfolio optimization would be the obvious, working out what proportion of assets, liabilities, that one should take on in order to maximize the amount of money one makes. So the papers that I've read that concern the portfolio optimization problem would encode the perfect state, or let's say the portfolio which maximizes the amount of profit in a ground state, and then use QAW or VQE methods to sort of find that ground state. But I'll be talking more about the proposals that I've read for a risk analysis or derivative pricing, which would use a quantum amplitude estimation approach. So yeah, both of the former 2 cases, you'd use a QAOA. And the underlying problem can be couched in terms of trying to find an expectation value in both of these 2 cases. So apologies to some of the SQMS Fermilab colleagues. They've seen slides similar to these over the last couple of months. But in the derivative case, let's say one enters into a simple futures derivative where parties agree to exchange an asset at a particular strike price K in the future. Let's say the asset's value at time t equals 0, so now, is S0. And at the maturation date of the contract, the asset's price would be ST at some time t in the future. Now, this evolution from price S0 to ST wouldn't happen deterministically, it does happen stochastically. Right, so the best we can do is try to work out what the probability is of the asset evolving from S0 to ST. And in this case, if this contract represents an exchange of assets, the buyer's payoff, so the amount of money the buyer will make, will be just the difference between the actual assets price and the pre-agreed upon strike price. And derivatives pricing concerns itself with working out the expected payoff, the expectation value here. Similarly, or maybe not too similarly, in a risk analysis perspective, as I mentioned, one is concerned with trying to find the variable at risk, but this can also, the variable at risk value, which would represent the lowest 10% quantile. But in this case, one could also couch this in terms of finding an expectation value of some function, but this function in this case is would just be an indicator function, which would be like 1 all the way over here and 0 for profits or loss values greater than the var value. But when one starts, one doesn't know what the ideal var value is. So you would just choose one randomly, then tailor a quantum circuit based on a particular X value, work out what this expectation value is, so the cumulative distribution function based on a chosen X, compare it with whatever your confidence interval is, and then do a bijective, or I mean a bisection search over different values of X until you get closer and closer to this inequality. But a bisection search is logarithmic in complexity, so any advantage would come from the quantum case. So I'm going to go through this very quickly. I'm sure a lot of people would know a lot about quantum amplitude estimation, but to solve these two problems using a QAW approach, one would first have to come up with an efficient method of loading the probability distribution, which you could know from, let's say, modeling, or it could be implied by the data. You would load this probability distribution into a register of qubits, then use a series of controlled Y rotations to load your, in superposition, load your function into the coefficient of some ancilla qubits. Do this process in parallel over all of these different states in the superposition, which is this loading the probability distribution and doing these controlled Y rotations. I've called this operator A cap here. And then finally, one would use typical QAE to try and estimate the probability of measuring the ancilla qubit to be in the 1 state, which would give you this an estimator for the expectation value that you've been trying to find. So now I work at the SQMS Center at Fermilab, and one of our proposal is that we should be able to, or we're aiming to build a qudit-based quantum computer. So after reading a couple of these papers, these finance papers, I wondered whether an analogous approach exists for a qudit-based quantum computer in theory. And obviously, at the end of the day, when we try and test these things in real life, we'll be constrained by the fundamental gates and operators that we have access to. And this is probably all still a few years into the future. But at least from a theory perspective, there should be an analogy for this sort of derivative pricing and risk analysis, these algorithms in a qudit-based platform. So yeah, replace every qudit with or qubit with a qudit. Each of the qudits would lie in a d-dimensional Hilbert space. First step, load the probability distribution into the coefficients of some register of qudits. Now we know that in a qubit case, this to create an arbitrary unitary would need an exponential number of gates. However, a lot of the probability distributions which one encounters in finance are typically log normal or of a log concave nature. And therefore, it's been proven in this paper that it should, at least in theory, be easy to create an operator to load the probability distribution into this register of qubits. or qudits in this case. However, a lot of real world data wouldn't follow a log concave probability distribution, and therefore it becomes important for people to start considering other methods of creating an efficient way of loading the probability distribution. And people have, I think this is still an open question, and I believe people have considered generative networks or machine learning approaches. But let's just assume that we can load this distribution. The second step is then to, in parallel, use a series of controlled Y rotations to load our function into the coefficient of some ancilla. So for a futures contract, the function which we want to, whose expectation value we want, is simply just a linear function. And so this can be loaded using a series of controlled Y rotations, where I'm assuming here the Y rotation is in the let's say the 0, 1 subspace. So this could in fact then be a qubits. The hardware at the end of the day that we create will constrain what fundamental gate set we have access to, but at least not constraining yourself in any way. This, I guess, should be a possibility. For the variable at risk calculation, you would need to add sort of a comparator subroutine in order to, in parallel, compare the profit or loss continuously in parallel in the superposition against what we would, the randomly chosen var at risk value that we chose is. However, there is, in a qubit case, there is a sort of comparator using a series of adders and whatnot, which keeps track of whether there's a carry bit when making the comparison here between I and X. And in the qudit case, and there is an analogy for qudits also. And then finally, let me just quickly go through the slide. Once you've loaded the distribution and done a series of Y rotations, then you would use typical quantum amplitude estimation to estimate what the expectation value is of, or what the expected value is, coefficient is of the ancilla being in the 1 qubits on the 1 computational basis state. And there is a QAW circuit analog for qudits compared to the simple qubit case. So after just sketching some rough notes and going through this, I wanted to see, or try to see whether there's any advantage for using qudits over qubits. And I can see about 3 for our SRF platform here. Firstly, there's the obvious that qudits can hold more information than qubits, obviously everything else being equal, and hopefully potentially can process more information. Secondly, in the qudit quantum amplitude estimation circuits, the error between the true value which we're trying to work out, so here on the left, and the estimator which the qudit QAW algorithm gives us, scales a little bit more favorably for qudits compared to qubits. So for qudits, the error scales as 1 over d to the m, where d would be the Hilbert space dimension and m the number of qudits we have access to, whereas the scaling would be 1 over 2 to the m for qubits. And then finally, I'm told that a lot of the really hardware experts that I'm busy learning things from claim that we should, in theory at least, be able to achieve all-to-all connectivity between the qudits in our SRF platform. And this would obviously make the circuits a lot shorter. You wouldn't need these complicated swap gates that you see in a lot of the 2D architectures. And yeah, I think that's me done. Thank you.
Thanks, Nick. Any questions? Josh.
Just in that advantage slide, you showed that the error scaling, the second bullet point, the error scaling for qudits might be favorable in some instances. I just did a sanity check of imagine you've got a 4-dimensional Hilbert space, so 2 qubits, so m is 2, you get a quarter, and you might imagine you've got a qudit, 1 qudit, and that's m equals 1 in that case, and there's a quarter. But I imagine at some point there's a trade-off, and do you know when that is?
No, I'm still trying to figure it all out.
Okay.
I mean, I'd love any insights if you have any idea.
Yeah, no.
Other questions? All right, thank Nick. Let's thank Nick again.
Thank you.
So before we all break up, thanks for coming. I think this has been a nice workshop. And, I think a few things we kind of hit the number of people to have and the amount of time to have conversations. We tried to make it so that there'd be plenty of time for people to, potentially generate collaborations and talk to each other. But logistically, it wouldn't have been possible without Ivan, who kind of has overseen a lot of it. A lot of his expertise with Squint has kind of, helped us out. And then practically, I think we have Dwight here. So Dwight here. And, so Dwight has done all the boots on the ground work, and, that made it, so that our catering all worked out and our banquet all worked out, and, all of the details that were important. And I don't think she's here, but Leanne Yanabu,
Yes.
Worked on, she must have done, 100 different modifications of the website as we got new information on it and stuff. So I'd like to say thanks to her as well.
And also a special thanks to Pablo Poggi for really going up and beyond the call of duty here to make an incredibly smooth, that this was the best hybrid meeting ever. So thank you, Pablo, for. Yeah, welcome back next time. Well, maybe we'll see you at Squint, which is going to be in Berkeley this year on October 20 through 23. So stay tuned for that. It's always a great meeting, and we appreciate Lionel's participation and now the extended community here. So have a good rest trip back home, everyone, and thanks for coming.
Yep. Safe travel.
Thanks to Andrew and all the co-organizers at the QSC and SQMS who really did a tremendous job to put this together. So special thanks. Okay, sayonara on Zoom. End meeting. Click for all.